Well, here we go on Unit 1B, Lesson C, Projectile Motion. Our learning targets for this lesson will be for you to explain why two simultaneously launched objects will land together when launched in three different ways. You want to be able to, at the end of this, to be able to write down expressions for horizontal and vertical components of velocity and sketch or identify graphs of those components. And then solve problems involving projectiles launched horizontally, projectiles launched at an angle, and involving relative velocity. To start with, let's look at two questions. Question one is, during a movie stunt, a car is driven straight off the side of a bridge to a river below. At the same moment that the car leaves the bridge, our movie hero who is hanging off the side of the bridge lets go and drops straight down. Who hits the river first? So this is the situation. We've got the car that will be heading horizontally off this bridge and down into the water below. At the moment that that car is right here at this point, exactly where the person is, person drops, car launches horizontally, and we're assuming that they are launching from the exact same point. Okay, which of these objects would hit the ground first? And then we extend that question to say that during that same movie, a different stunt involves driving two cars off a cliff at exactly the same time, where one car is driven off the cliff at a certain speed while the other is driven off at 4 times that speed. So which car hits the ground first? So I want you to keep those questions in mind as we go through this lesson. So projectile motion involves projectiles. And a projectile is any object that falls through the air. As it falls, it follows what's called a trajectory, which is simply just a path that a projectile follows. So in a real-world situation, any projectile is going to follow a path that's not quite a parabola, okay, because of air resistance. All the problems that we're going to work with, we're going to assume zero air resistance, giving us a theoretical path of a perfect parabola for our projectiles. So let's look at the trajectories of two balls released simultaneously. Here we have two balls that have been released simultaneously. The red one falls straight down. The yellow one is launched horizontally so that it has a component of its velocity in the x direction. Okay, the red ball's velocity all points straight down, all in the y direction. So you can see for both launched balls, okay, the vertical separation increases as they go down, and it increases at the same rate, showing us that they have the same downward acceleration. But let's take a look here at the separation, the horizontal separation between different points of the yellow ball's trajectory. And we see that it does not change. That horizontal part of the yellow ball's trajectory does not change. See, the yellow ball has a component of velocity in the x direction and in the y direction. It has both a vx and a vy. That vy is subjected to an acceleration that points straight down. So it has an acceleration that's equal to g. Okay, in the horizontal direction, because this separation does not change in that horizontal direction, we can see that from this picture. That indicates to us that the x velocity is constant. So if we were to draw out, here's that yellow ball. It has a vy straight down. It has a vx perpendicular to that. And the thing that vectors that are perpendicular to each other act independently. They don't affect one another. Okay, so we can look at a projectile motion. We can look at it in those two different dimensions, independently of each other. So we can look at the vertical motion of a projectile using our kinematics equations, where we plug in our acceleration of g. And in the horizontal direction, because there's no acceleration, that horizontal velocity is constant, we simply use the constant velocity equation. This is really similar to the example where we had the boat going across the river. Okay, as the boat traveled straight across the river, and the river acted acted perpendicular to the boat's velocity, we ended up with a final velocity, a resultant velocity, at an angle. Same thing applies in any projectile motion. So that what we're able to do is split the velocity of any projectile into its two components, Vx and Vy. We'll be able to find Vy typically by V sine theta, and Vx typically by V cosine theta. So the important concepts for projectile motion is that there's no acceleration in the horizontal direction. That motion is always constant velocity in that horizontal direction. In the vertical direction, projectiles accelerate at g downward. So we can see if we launch an object, say, completely horizontally, as it falls, it accelerates down. It does not accelerate out. And we call this, the downward part of the motion, there's its height. We can call the horizontal part the range. Okay. Now there's basically two types of projectile motion problem that we'll be dealing with. Okay. There's what's called horizontal launch, and there's what's called angled launch. This picture here is indicating a horizontal launch problem where it's showing our projectile coming down with increasing velocity in the vertical direction, constant velocity in the horizontal direction. So in problems with projectile motion with horizontal launch, the horizontal velocity is always constant. The initial vertical velocity is always 0. The acceleration in the vertical direction is always equal to g. So, when we have a problem that's we've launched something horizontally, there's three basic ways that problem can be presented. Okay, we can give you the height and initial horizontal velocity and find the horizontal distance. We can give you the height and the horizontal distance and find the initial horizontal velocity. Or we can give you the horizontal velocity and horizontal distance and find the vertical distance. In order to solve this first type, now this may not be given explicitly in a problem. Maybe it's something that you found from another part of a situation earlier in that problem. Say the object started back here on a ramp, it comes down off this ramp, rolls off to the table below. Okay. If you have to calculate the speed at the bottom of the ramp, right, then that's basically giving you that horizontal velocity. So when you're in a situation of a horizontal launch problem and you've been given you've got the horizontal velocity, you've got the height, and you're looking to find the range, you're just going to use that second kinematics equation to find the time down, and then use constant velocity to find that range. If you're given the heights, if you're given the height and the range, again, use the second kinematics equation to find the time down, and use the constant velocity equation to find the Vx, the horizontal velocity. Now you have to remember that when we're using this second kinematics equation, we're looking in the vertical direction, and that initial y velocity is always 0. Okay. Now when you've been given the horizontal velocity and the range, okay, you need to find the height of the table or the cliff or whatever it is. You're going to first use the constant velocity equation to find the time down, and then use a kinematics equation to find the vertical height. Look back at this situation right here. This is the situation we're looking at. We're going to use our second kinematics equation to find the time down, and then use constant velocity to find Vx. So let's look at a problem involving this horizontal launch business. Okay, we've got the Royal Gorge Bridge in Colorado, rises 321 meters above the Arkansas River. So here's our bridge sitting here. It rises 321 meters, so delta y is 321 meters. And we kick a rock horizontally off the bridge this way. And the magnitude of the rock's horizontal displacement, the range then, is 45 meters. So delta x is 45 meters. And we need to find the speed, Vx, at which the rock was kicked. Okay? Now, in that we don't know. We're looking for the horizontal velocity. We have already the vertical velocity, Vyi, of 0 meters per second. Okay? Because in that vertical direction, there's no initial velocity. Remember, we can look at the velocity vectors independently of one another. So then, if we, okay, so when I write this equation out, notice now that I am using the y component to show my displacements, and I'm using Vyi. This is, I'm making it very explicit that I am looking in the y direction. I'm not using an x here because I'm not looking in the x direction. I've got two different directions that I have to look at, and I have to distinguish between them. So my YF, now I can put my 0 point, my 0 vertical, I can put that at the top of the cliff, or I can put it at the bottom of the cliff or a bridge. Okay? If I put it at the bottom of the bridge, then that is YF. If I put 0 at the top of the bridge, that's YI. If I put YI as 0 at the top of the bridge, that's going to make YF negative down here, and I have to indicate that in my calculation. If I make YF 0, then YI can start as positive, and then when I subtract it over to the other side, it becomes a negative. So either way, it just, however you choose to put that together is fine. So when I make my substitutions, it looks like this. I'm looking in that vertical direction, so my initial y velocity is 0. And when I run through the calculation then, I end up with a time of 8.094 seconds. Okay? So now from here, it's just a matter of using my constant velocity equation to find my Vx. So I'm looking for my launch velocity here. And as I run through that calculation then, I end up with 5.6 meters per second. Alright, so now let's look at a situation where we're launching a projectile at an angle. So this would be situations like, a cannon launching a cannonball, or, a slingshot shooting a stone, something like that. So with this situation, right, the horizontal and vertical components of that initial velocity, they're still independent because they're perpendicular to one another, except now the initial velocity in the y direction is not 0. We have some sort of initial velocity in the y direction. And what this picture indicates to us is that as this projectile goes through its trajectory, we've got, this is what we would call its initial velocity, and then we have a component of that velocity in the x direction, and we have a component of that velocity in the y direction. So as we look at this, we notice in that horizontal direction that Vx always stays constant. That Vy decreases as it goes up, gets to 0 as it passes through 0 as we reach the top of our trajectory, and then increases on the way down. Okay? So as long as that projectile is in the air, it's going to move horizontally with a constant speed. It'll accelerate downward at a constant rate of g. At the top of its path, the vertical velocity will be 0, and the final vertical velocity will be equal to the initial vertical velocity, but point in the opposite direction. So it's really important to grasp this concept of independent perpendicular vectors. Okay, and now it's not just true for just velocities, but it's true for any vectors that are perpendicular to each other, they're independent of each other. Okay, so we can have this component of our velocity be constant while the other one accelerates. It's also keep in mind that when you begin to look at problems, if you're told that the launch velocity or the initial velocity is 5 meters per second, okay, that's talking about this initial velocity. So if we've got a problem where we've got something launched at an angle of 30 degrees at 8 meters per second, okay, so it's talking about this resultant velocity, and then what we have to do generally is split the velocity, that initial velocity, into its components, Vx and Vy, and then solve that problem looking at the vertical direction independently of the horizontal direction. Okay, keeping in mind that with any projectile motion, right, the time in the horizontal direction is equal to the time in the vertical direction. Okay, it doesn't take a projectile more time to go out as it does for it to go up and down. Okay, and also we can also look at these angled launch problems from as two different problems. We've got like a constant velocity problem here, and in this picture we've got a problem where it's a free fall where it's gone up and back down. If we could take this cannon, right, and we were to put it on top of a building where we now have this launch going down further this way, right, then this is the same as having a constant velocity problem in the horizontal direction and a free fall problem where we've got the object going up and back down further. Okay, so let's look at an example. Here we got a zookeeper finds an escaped monkey hanging from a light pole. She aims her tranquilizer gun at the monkey. She kneels 10 meters from the light pole, which is 5 meters high. The tip of her gun is 1 meter above the ground. At the same time that the monkey drops a banana, the zookeeper shoots. If the dart travels at 50 meters per second when it's launched, will the dart hit the monkey, the banana, or neither one? So here's a pictorial representation then of this situation. We have the launch velocity here. It's been launched at some angle. The range then of our projectile will be 10 meters. The monkey is sitting 4 meters above, and then the projectile is launched 1 meter above the ground. Okay. So the first thing we need to do is we need to figure out this angle of launch, and we're going to use the tangent function to figure out the angle of launch. Doing that gets us an angle of launch of 21.8 degrees. So the next thing we want to do is resolve our velocity, our initial velocity, into its Vx and Vy. So to find Vx, we use V cosine theta, plug in our angle, our initial velocity here. We get a x component then of 46.42 meters per second. Vy involves using V sine theta, and we end up with 18.57 meters per second in the y direction. Now, since we know our range of 10 meters, we've got our constant velocity in the horizontal direction, we can use our constant velocity equation to figure out the time that it takes for this projectile to travel to its destination. And doing so shows us that we end up with a time of 0.215 seconds. Okay. Now what we want to do is we want to use kinematics equations to figure out how far, like the banana, would fall. Okay. So we're going to look specifically at the banana at this point. Okay, so what we're looking at then is I'm setting my initial velocity in this case as my initial position is 0 up on the light pole. My initial velocity in the y direction is 0. and I'm looking to see where this banana is going to be at the same time that the dart goes its horizontal distance. Okay, because in that same amount of time, the dart is going to go up and down. Okay, and what we find here is that our banana falls 0.227 meters in that same amount of time. So the next thing to do is figure out how high the dart goes in this same amount of time. Okay, so we know then that the banana is going to fall this 0.227 meters. We want to find out how high the banana is going to go in that same amount of time. So setting my initial position for the dart at 0, well, I've got my initial velocity in the y direction, the amount of time that it takes to go the 10-meter range. I end up with a height of 3.77 meters for the banana. So then, if the banana begins at 4 meters above the launch point and drops 0.227 meters from that launch point, it is in the 0.215 seconds, it is 4.77 meters above the ground. The dart starts at the ground, and if it is 3.77 meters above launch point at in that 0.215 seconds, and that launch point is 1 meter above the ground, then that means in that 0.215 seconds, the dart is 4.76 meters above the ground. Therefore, the dart hits the banana. Okay, so that's projectile motion, and we will see you in class.